You cannot build a massive 50-story steel skyscraper using the informal methods meant for a simple backyard shed. That physical reality translates directly to digital engineering. A small, isolated application might survive its initial launch without formal planning, but an enterprise-level system requires rigorous modeling, well-defined processes, and structural discipline to function. This discipline is software architecture. It is the deliberate design and documentation of a system's high-level structures, the specific software elements, their distinct properties, and exactly how they relate to one another. Consider a sprawling legacy network, like the Indian Railways routing platform. Because the original documentation is lost, a new developer might look at the codebase and conclude that it simply has no architecture. That is impossible. Every functioning system has an architecture. When an architecture is not deliberately planned, it becomes an accidental architecture. The code grows organically over time, layering feature upon feature until the internal connections form a rigid, highly unstable web of dependencies. Relying on these unformulated, accidental structures leads to a predictable outcome. The moment developers attempt to introduce modern modifications, the rigid internal dependencies cause new features to break old ones, effectively freezing the system's development. To avoid that stability trap, we have to separate what a system does from how well it does it. This is the split between functional requirements and non-functional requirements. A functional requirement dictates a specific task the software must perform. In a railway application, a functional requirement is the user's ability to input a destination, select a date, and successfully book a train ticket. The non-functional requirement dictates the operational constraints of that task. It demands that the system process 10,000 of those ticket bookings concurrently, without a single server timeout or data collision. These constraints are known as architecturally significant requirements, or ASRs. They are the strict metrics governing performance, security, availability, and scalability. Developers write the localized code to fulfill the functional features. Architects, however, select and map broader structural patterns across the entire application, specifically to guarantee that the ASRs hold up under maximum load. Without prioritizing architecturally significant requirements at the blueprint stage, a system might execute perfectly in an isolated testing sandbox, only to collapse immediately under the strain of real-world traffic. Let's test that theory against a high-load scenario, a multiplayer gaming software. The application must support thousands of simultaneous players across varying devices, continuously sharing high scores and real-time game states. There are 3 distinct structural patterns we could deploy to solve this challenge, each prioritizing a different outcome. First is the layered architecture. It organizes the system into distinct horizontal tiers, heavily restricting dependencies to improve overall modularity and ease of maintenance. The trade-off is speed. In a layered model, every user action must sequentially traverse multiple tiers to reach the database and travel all the way back. That journey introduces latency, rendering it completely unviable for real-time gaming. Next is the MVC, or Model View Controller pattern. This approach strictly separates the back-end game logic from the user interface. MVC provides excellent flexibility for developers building distinct visual interfaces for mobile phones, tablets, and desktop monitors, but it lacks a native mechanism to synchronize state across thousands of independent external clients. Finally, we examine the broker pattern. Here, an independent routing hub acts as the mediator, dynamically managing distributed network communications. The broker is critical for massive multiplayer environments because it seamlessly coordinates the real-time state updates across thousands of highly variable client connections, keeping every player completely synchronized. Architectural design relies on choosing between competing structural advantages. The architect must willingly sacrifice the strict modularity of a layered approach to secure the real-time performance required by the users. This diagram outlines a different structural challenge. Here we have a flight aggregator application.
Its primary function is to seamlessly interface with disparate third-party airlines and legacy banking vendors to complete user transactions. To orchestrate these isolated external services, the system utilizes a service-oriented architecture, or SOA. The web service broker acts as the core mediator, handling message routing and format conversion between the aggregator and the external providers. By keeping all of these components loosely coupled, SOA ensures that when a new payment vendor is added to the network, the engineering team does not have to rewrite the aggregator's core backend logic. This documentation reveals a severe operational tension. Heavy background data analytics queries are degrading real-time ticket transaction performance. To resolve this, the architecture dictates asynchronous input and output calls to isolate the conflicting workloads. By implementing message queues, the system effectively buffers the primary database. Real-time ticket transactions are processed instantly by the main server, while complex, resource-heavy analytics compute safely in the background on isolated worker processes. A mature architecture anticipates data bottlenecks. It deliberately separates conflicting workloads to maintain total system equilibrium under stress. Let's apply these scaling principles to a physical industrial process. A waste management company tracks and empties thousands of commercial recycling containers across urban environments. The digital challenge requires a central cloud application to optimize routing schedules for dozens of different municipalities without exposing their private, proprietary data to one another. The solution is multi-tenancy. One global cloud application hosts a logic, while securely partitioning the internal data into exclusive silos for each individual client municipality. Because physical events, like a holiday weekend causing containers to fill rapidly, create unpredictable spikes in data traffic, the system utilizes automated orchestration to instantly scale its compute resources. By engineering these cloud services to be completely stateless, the architect minimizes memory usage. This optimizes the system's capacity to load balance those traffic spikes seamlessly across the available servers. Effective cloud implementation depends on designing applications that can natively exploit elastic, automated scaling. Designing a new system is only half the discipline. Architects must also proactively diagnose anomalies in existing platforms. Consider an e-commerce platform running a promotional pricing engine. The business logic strictly authorizes a 15% discount exclusively for users paying with an HDFC Visa card. During an audit, an anomaly surfaces. Users presenting unapproved SBI MasterCards are successfully bypassing the restrictions and triggering the identical 15% discount. This is not a simple coding typo. It represents a critical breakdown in the system's structural authorization flow. The logic validating the payment type has become detached from the logic applying the final price. This is the reality of architecture conformance. As new code is pushed to production, it often begins to drift away from the security boundaries defined in the original blueprint. When systems are permitted to operate outside their designated architectural boundaries, invisible logic flaws compound into severe financial and security liabilities. To trace the exploit, the architect must immediately deploy strict audit logging across the entire transaction pathway. An immutable audit log records the exact routing history, payload, and origin of every network request. It allows the engineering team to reconstruct the exact path the malicious request took to bypass the authorization check. Once identified, the permanent structural fix requires establishing a centralized API gateway directly upstream from the vulnerable pricing database. This acts as an intercepting filter. It rigidly enforces authorization control, shielding the internal business logic by actively rejecting unauthorized queries before they can execute. Software evolution moves through distinct phases. We transition from accidental, undocumented mudballs to selecting comparative patterns, and finally to enforcing structural boundaries to stop progressions. A digital system's longevity and security are dictated not by the localized elegance of its code, but by how strictly the final build adheres to its architectural blueprint.